AC signals change continuously with time, making circuit analysis more complex. Instead of tracking every instant, we can represent sinusoidal signals in a simpler mathematical form. In this lesson, we will learn phasor representation and how it transforms AC analysis into a frequency domain problem. A phasor is a mathematical representation of a sinusoidal signal that transforms a time-varying waveform into a rotating vector in the complex plane. Instead of analyzing voltage and current as functions of time, phasors allow us to represent them using magnitude and phase at a given frequency. This transformation simplifies AC circuit analysis by removing explicit time dependence. A sinusoidal signal, such as a voltage waveform, can be represented as a constant complex number that encodes amplitude and phase information, while the time variation is implicitly handled by a rotating reference. Phasor representation is fundamental in circuit theory because it converts differential equations in the time domain into algebraic equations in the frequency domain. This makes complex circuit analysis significantly more manageable and forms the basis for modern AC system design. Phasors are derived from Euler's formula, which relates sinusoidal functions to complex exponentials. A sine or cosine waveform can be expressed as the real part of a complex exponential function with a rotating phase factor. By removing the time-dependent exponential component, the remaining complex amplitude becomes the phasor representation. This phasor contains both magnitude and phase information, which fully describes the sinusoidal signal at a fixed frequency. This transformation allows engineers to replace calculus-based circuit equations with simpler algebraic expressions. As a result, impedance, voltage, and current relationships can be analyzed using straightforward complex arithmetic. The main advantage of phasor representation is simplification. In the time domain, AC circuits often require solving differential equations due to capacitors and inductors introducing time-dependent behavior. In the phasor domain, these elements are represented using frequency-dependent impedance, eliminating the need for time-based differential equations. This conversion allows circuit analysis to focus on magnitude and phase relationships instead of instantaneous waveform behavior. It becomes easier to predict how signals propagate through complex networks and how different components affect phase shifts and amplitude changes. Phasors also make it easier to visualize how AC systems behave at a specific frequency, which is critical for understanding resonance, filtering, and signal transmission. In practical engineering, phasor analysis is widely used in power systems, electronics, and communication circuits. Engineers use phasors to analyze voltage and current relationships in AC networks without dealing with time domain complexity. Power system engineers rely heavily on phasor representation to study load flow, stability, and phase relationships in large electrical grids. In electronics, phasors simplify the design of filters, amplifiers, and signal processing circuits. This method is especially useful when dealing with steady-state sinusoidal signals, where only frequency, magnitude, and phase matter. It provides a powerful abstraction layer that simplifies both analysis and design. In RF engineering, phasor representation is essential because all RF signals are sinusoidal and frequency-dependent. Using phasors allows engineers to analyze signal behavior in terms of amplitude and phase rather than time-domain waveforms. This is critical for impedance matching, signal reflection analysis, and network design in high-frequency systems. Phasors also enable accurate modeling of how signals propagate through transmission lines and circuit components. Understanding phasor representation is a key step toward mastering frequency domain analysis, which is the foundation of all RF and microwave engineering systems. In this lesson, we learned that phasor representation converts time-varying AC signals into simplified frequency domain vectors. This transformation allows complex circuit equations to become algebraic and makes AC analysis much more efficient. In the next lesson, we will explore impedance concept and understand how resistance, inductance, and capacitance behave in the frequency domain. If you found this useful, like the video, subscribe, and follow for the next lesson.